So a lot of the mathematics of finance is pretty difficult mathematics, stochastic calculus, uh, there's partial differential equations, but it doesn't all have to be super high-end math. So just as a little break, we can look at something a little simpler, the mathematics, and that's using first order linear difference equations in finance. And this will be more aimed at personal finance because it's a fairly simple method. So what we're going to get are, think of them as kind of back of the envelope type calculations, but they're it's powerful mathematics to have. So first off, let's unpack what this means, the first order linear difference equation. Here's the most general version of it. A and B are constants. The x sub n, what I mean by that, that's the amount in your account or your investment at time n. Now, in my examples, the n is going to be the year number, year one, year two, year three. But if for other applications, it could be daily. If you're getting daily interest, maybe those n's are counting the days. So it's the time step. And so x sub n plus 1 would be the next year. So n is the nth year, and nth plus 1 is the year after that. So it's a way of writing down, keeping the years in order. But we don't necessarily do any mathematics with the sub n. It's just to keep the n's in order. So equation, well, because it's an equation, left side equal to right side. Difference equation as opposed to differential equation, or, well, they're related, but a difference equation is we've got the next value is a function, in this case a linear function, of the previous value before it. So difference equation, um, that'll come up in it'll be more clear why we call it a difference equation in a following video when we start to solve these difference equations, this linear difference equation. But right now, think of it as a discrete equation. I plug in a value for how much money I have in my account this year, the nth year, I plug it in here. I multiply it by A, I add B, and I get the amount of money in my account the next year, the next time step. So linear, because this function is a line, is a linear function. Think back when we did lines in elementary school, y equals mx plus b. To get the y value out, you take the x value, you multiply by m, the slope, and add b. In this case, instead of writing m, I'm writing a. I'm just following the traditional notation, but it's a linear function. The next value in the sequence is a linear function of the previous value in that sequence. First order, well, first order refers to the fact that I only need one value to get the next value. There's only one step. If it was a second order, then I would need how much money I had this year and how much money I had the year before that, plug it into some formula to get how much money I get the next year out. But it's first order because, well, practically, because the difference between the highest order term, n plus 1, and the lowest order term, n, is 1, so it's a first order. But anything that can be modeled where you take your value in your sequence, multiply it by A, and add B to get the next value, can be modeled with a first order linear difference equation. The examples that I'm going to show here are all personal finance type examples. So let's start with that then. Let's look at our first example. So say we have an initial investment of $300 and we add $50 at the end of each year to that investment. The account earns 5% return each year. So the initial investment is $300. So that's how much money I have right at the beginning. So I'm going to call that X naught. That's our initial seed value. Now think what happens to that X naught. Oh, we got to get the timing set up. I'm going to add $50 and then they're going to give me the interest, or do they give me the interest and then I add the $50? We're going to assume that I get the interest 5% and then I add the $50. So x sub n is how much money I have at that nth year. Now, the first thing I do is get interest. So they're going to add 5%. I think I'd like to think of it as they take my money and multiply it by 1.05 if I'm getting the 5%. The 1 keeps the money I already have, 1 times x of n, and the 0.05 is the additional 5%. We could write that as x of n plus 0.05 times x of n, but we would simplify to be 1.05 times x of n. And then I add the $50, and that's how much money I would have for the next year. I take the money I have, get my 5% interest, and then add $50. So I've expressed this as a first order linear difference equation. The A is 1.05, the B is $50, 50. Now, if I wanted to figure out, all right, how much money do you have in like 4 years or 8 years or something, then I know I start out with 300, and so that's X naught. So at year 1, then how much would I have? Well, I'd take 5% add to my 300. So I take my 300 and multiply by 1.05. So I get, well, 5% of 100 is 5. I've got 300, so I add on $15. This is going to end up being $315, and I add in the $50. So this should simplify to be $365. Yeah, the 315 plus the 50. So that's how much I would have after one iteration of this first order linear difference equation. And now if I wanted to know what x sub 2 is, well, I'd have to go through the process again. I'd have to take that $365, multiply it by the 1.05, and then add 50 to get x sub 2. And then x sub 3, I'd have to sort of chug through the process. This is the kind of thing that screams out for a spreadsheet. So let's do that. Our initial value is $300. What happens to our money? We take the 5%, 1.05, times the value we had before, and then we add $50 to it. There's our 365. That 1.05, that's the A, the 50, that's the B. Those are constants, those are parameters, those are constant parameters through the problem. Now I can just copy this down, and each cell is taking the cell before it, multiplying by 1.05 and adding 50. So I start off with 300, and I can see that I get 365, etc. And we can graph this if we want, and sure, why not? It looks linear. Well, no, on second thought, it looks a little bent, right? It should be a little bit bent because as I get more and more money, that 5% starts to eclipse the $50 that I put in. So the difference equation is linear, but the graph should not be linear. If I extend this, let's keep this investment for years and years and years and see what happens. And add on, make a new graph of this. Okay, now it's clearly not linear. I'm getting what's looking like exponential growth. So how is the linear part of this difference equation, how is this linear part expressing itself? Well, let's look at the difference. The difference in how. So in other words, like how much money did I make? Well, I ended up with 365. I put in 300, so I made the $65. So this column is putting in how much money I make. Now that's including the 5% and the $50. Of course, the $50 starts to become less and less important as time goes on. If I were to graph this, so the difference, the profit, let's say, that's not linear either. So how does that linear part, because it is a linear equation, when we looked at it, the next value is a linear function of the last value. Why aren't I not seeing anything linear in the graphs? Why isn't it a line? Well, because I'm not looking at I'm not looking at it in a linear way. If I think about this as the line, a y equals mx plus b, the input value would be your x sub n, and your output value would be your x sub n plus 1. Let's look at it that way in the spreadsheet. That will be our line. So let's go back to our values. I'm going to get rid of this, and this is our, if this was our input value to our equation, our line, our output value was the 365. So that's this value here. So let's make this a little bit more, let's make this look more like we would have saw in elementary school, in high school, middle school, wherever we do this. That would be the x value, and that would be the y value. The y value, of course, I'm just getting from the next value. But now, so I'm using this series as both the x value and the y value. But when I graph them as a scatter point, x, y points, there's my line. So if the fund is governed by if the investment is governed by a first order difference equation, then if I make x, y points out of this year's money and next year's money, it should lie on a line. The slope of that line is the 1.05, and the intercept of that line is the $50 in this case. Okay, let's go back to another example. This is very similar, but the only difference being that initial investment's $300. I add $50 at the beginning of each year, and then the account earns the 5%. So what's different between the first example and the second example? Well, they're very similar, so I'm going to copy paste this because I can just modify. But the difference is that the first thing that happens to my money is I add the $50 and then I get the 5% interest. So here I get the interest and then add the $50. This second example, I add the $50 and then get the interest. Now, this second example is going to be better for me because that $50 earns interest earlier than in the first example. If I were to expand this out, so I were to clean this up, then I can see that it does make a first order linear difference equation. Again, the A is the same, but the B is now $52.50. Yeah, because that $50 earns the 5% interest. That's the $2.50 extra here. But I still get an A and a B. It's still being modeled. It's still being templated by this first order linear difference equation. Let's do a couple more examples. In this next example, I earn 7% return each year, but I'm taking money out. So however much money I have, the first thing I'm getting is the 7% interest, and then it says taking the $200 out at the end of the year. And this is how much money I would have in the next year. So what's the point of this example? The B is negative. So the A's and the B's, they don't have to be, as far as the math is concerned, they don't have to be positive numbers. They could be positive numbers or negative numbers. In this case, the B is a negative number. Now, what I don't have here is I don't have an initial investment. I don't know what X naught is. Now, if I'm making 7% on my money, this if this 7% that I made, the profit, is more than the $200, then the account will grow. If it's less than the $200, then I keep taking out more money that I make every year, then the account shrinks down to nothing. So this question of is there an equilibrium value, let's figure that out. An equilibrium value would be some number, some account number, some value, undo, that when I put in here, so let's call this equilibrium value X bar. Some people put X sub E for equilibrium. I'm going to put X bar. Now, if I put the equilibrium value inside the equation, I get out the equilibrium value. That's what it means to be an equilibrium value. So it would be the amount of money that I get the 7%, then subtract the 200, and I'm back to that same amount. So we can just solve this. So our equilibrium value then is $287, $2,857.10. What does that mean? Well, let's move that over. I would get 7%, and that 7% must bring this up to $3,057.10, and then I take out the 200, and then I'm back to the 2857.1. So it's an equilibrium value. Let's look at that in the spreadsheet. So it was 2857.1, and okay, I'm just concerned with now what happens to my money. I'm getting 7%, so I multiply by 1.07, and then I'm subtracting $200. So I don't want to graph anything. I'm not worried about graphing anything right now. Oh, now I was trying to show you that this stayed at equilibrium, but it's drifting smaller and smaller. I'm losing money here. That's because this is an equilibrium, but it's not a stable equilibrium. And this number that I asked the machine to solve for me, it's not an exact number. It gave me a decimal approximation. Let's get the exact number, because this 2857.1, that doesn't appear to be the equilibrium. The spreadsheet's not confirming. So if I were to solve for x of n, x bar, I'm going to bring this over to the other side. Let's bring the 200 over to that side of the equation, and then this would be minus x of n, which would be just 7% of x of n. Now, and then solve for the equilibrium, which would be 200 divided by 0.07. And I guess if we want to make this exact, that's the exact value. If I now it's a rational number, so I know it's going to have a terminating or repeating decimal. If I were to evaluate that numerically, yeah, it gives me that, but Now I'm at equilibrium when I put in the exact rational number. Okay, things that we learned from here. Let's go back. We know how to find the equilibrium value, plug in x bar, set it equal to x bar, and solve. We saw that our equilibrium value in this case was not a stable equilibrium value, because if I didn't start exactly there, it seemed to drift away, drift lower. Because I put in a slightly smaller number. If I put in because it was, the real equilibrium was 0.143, I put in 0.1. If I start off with something slightly bigger, so I'm just going to add like a little bit to it. Now it starts to drift bigger and bigger and bigger. So our equilibrium value is not stable. If I start there, I stay there, it's an equilibrium value. But if I start above, it starts to grow bigger. If I start below, it starts to go smaller. So it's not a stable equilibrium. Stable equilibrium would be one where if I was close to it, I would go towards it. That'll show up in our next example. Okay. You hide money in a Swiss bank account, charges a 1.2% fee at the beginning of each year. At the end of each year, you put in $15,000. Your initial deposit was $20,000. So I can see that X naught, that's my initial deposit, X naught is equal to the 20,000. What happens to my money, X of N? Well, in this case, they're charging me a 1.2% fee. So I'm going to multiply my money not by 1.012, but by 1 minus 0.012. So that's taking the fee out. And then I'm going to add to it $15,000. So they charge the fee, and then I put my $15,000. That's how much money I should have at the end of the beginning of the next year. If I simplify this, I can find my A and my B. Again, I'm trying to model this all with first order linear difference equations. And I see that my A is 0.988. Now I still get an equilibrium value. It's asking me here, is there an equilibrium value? Sure, we could find that equilibrium value by, okay, here's our equation. Plug in our value, multiply by 9.988, add 15,000, get the next value. To get our equilibrium value, it would be plug in our X bar, our equilibrium, and now, so I put in the equilibrium value, get out the equilibrium value. If I solve this, that should be my equilibrium value. And now let's try this on the spreadsheet then. Now this is a decimal number. Is it an exact decimal number, or is it an approximation like what happened to us last time? Let's figure that out. I take my money and multiply. We started out with 20,000. That was our X naught. I'm supposed to take the money that I have, multiply by 0.988, and then add 15,000. And that'll be how much money I have. It seems to be growing, growing, growing. And it's growing towards that 1.25 times 10 to the 6 number. It looks like it's going towards that equilibrium. So I started out below, and it's growing towards that equilibrium. if I started out above that equilibrium, so say 130,000. Now it's shrinking, or 1.25 million, sorry. I started above that equilibrium and now it's shrinking down towards that equilibrium. That's because they're taking away a percentage. They're taking away the percentage they're taking away is more than I'm adding in each time, the 15,000. It's shrinking towards that equilibrium. So let's go back to the point I'm trying to make here. We've still modeled this scenario with a linear first order difference equation. I've got the A, it's a fraction, and a B, it's a positive number. We found our equilibrium, and this equilibrium value appears to be a stable equilibrium. We seem to be going towards it. So let's finish up this by see if we can make a sort of a general. Here's our general linear first order difference equation. If I want to find that equilibrium, then I'm going to put x bar into the function and set it equal to the output and just solve. And actually what I'm going to get is b over 1 minus a. So this linear first order difference equation always has an equilibrium value of b over 1 minus a, which could be a negative number because a could be bigger than 1 and b could be a positive number. So the equilibrium could be negative. In the math, maybe that doesn't make sense with finance, but in the math it makes sense. Or b could be a negative number in the case we're taking out money, and a could be a positive number, in which case I get a negative equilibrium. So this is the equilibrium value. Does it make sense practically, or does it exist, let's say? Depends on if this x bar is positive or negative or not. But the equation has a equilibrium. Is that equilibrium stable or not? Well, we saw examples where it was stable, and we saw an example where it wasn't stable. So what are we going to have to do here? There's a couple of things that are going to have to come up in the next couple of videos. The first thing that has to come up is we need a better way to find out our future values than just plugging into a spreadsheet, getting if I want the 50th term, I need the 49th term. If I need the 49th term, I need the 48th term. So if I want the 50th term, I have to get all the other terms before it. Not too bad on a spreadsheet, but we're going to be able to generate a formula and solve a first order linear difference equation in general. And that will tell us something about the stability of the equilibrium in future videos. And then we can start to do some more interesting, more practical examples, answer some questions that you as a person and with personal finance would actually care about.